Hi, I welcome you all to the session of Geotechnical Engineering. I am Divya, Doctor Research Scholar from NIT Trichy, and I'll be handling this session in 3 consecutive sessions. First, while learning geotechnical engineering, we must be familiar with its definition and properties of soil. Soil exists in 4 different forms, like partially saturated soil, fully saturated soil, dry soil, and frozen soil. These are the soils. Which behave. The behavior of these soils may differ because of the presence of water and air in it, water, air, and ice in it. So the solids, while taking the soil capacity, shear strength capacity, or its flowability, or its consistency, everything, it's mainly depend upon its proportion on water and air. So I'll tell you this terms in detail. Partially saturated soil. Partially saturated soil will comprises of solids, water, and air. Solids is nothing but a solid particles which presents in the soil is solids. A soil is nothing. Soil is not only the solids; it's a mixture of solids, water, and air. So for a fully saturated soil, the voids between the solids is only comprised of water, and it will not have any air particles in it. And dry soil is nothing but it will be devoid of water, and it is comprised only of solids and air. Frozen soil, it has another phase of water, which is ice, and the outermost layer of water will be frozen, and the presence of ice particles will be formed in some types of soils, and this frozen soil has 4 phases in it. While seeing all the types, the partially saturated soil only having 3 phases. Fully saturated and dry soil has 2 phases, and the frozen soil has 4 phases. So a soil is soil whichever existing in the nature will be present in this will be present in the 3 phases or 4 phases, or it will be in 2 phases. We'll see it in detail. Okay. This is the whatever thing I have shown here. It is a 3-phase diagram, and here it is a 2-phase diagram. While we are dealing with a 3-phase diagram, we will typically know that it is a partially saturated soil. So the partially saturated soil will be comprising of water and air. First of all, I'll elaborate all the notations used here. So V is nothing but total volume of a soil. It is total volume. Okay. VV is nothing but the volume of voids. The voids is nothing but while arranging this solid particles, the gap between each and every solid particles, like for example, the soil is arranging in this way. So this will be the solids, and the spaces between these solids is nothing but voids, which is voids, and we are collectively taking this volume as VV. So as we know, volume of voids is a combination of volume of water and volume of air. So that's what is shown here. VW is nothing but volume of water, and V is nothing but volume of air. Okay, and this side it is VS is volume of solids. So the volume of voids may change, like while we are compacting the soil, or while the water content exceeds the volume, the VV volume of voids, it will change. It is not a constant parameter in a soil. However, the volume of solids will not change for a particular unit volume or unit something, whatever the things you are taking. If you are taking a 1 kg of solid, even if you are compacting a 1 kg of solid, this volume of solids will not change. While compacting, the volume of voids will be reducing, and while expanding or while loosening the soil, this volume of voids will be increasing. So so throughout this chapter, we don't want to consider about the volume of solids, since it is a very constant parameter. We don't want to we can use this volume of solids as a constant parameter while calculating itself. So it's a huge factor which have to consider in the while solving the problems. And this side I have mentioned about its weight. So this WD is nothing but weight of solids, and they have denoted as a WD, and weight of voids. This weight of voids is comprised of water and air. However, the weight of air is very much negligible, so we are taking it as 0. And while taking the voids, while considering the volume of voids, we are talking only about the weight of water. So the total weight of a soil is comprised of W is comprised of WS and WW only. So even if it is a dry soil, W is equal to WS. Hence, for dry soil, the amount of water will not be present. So W is equal to weight of solids only. So for a fully saturated soil, W is equal to weight of solids plus weight of water. That's all. And while considering the two-phase diagram, we already know that solids and water will be present. This condition is nothing but saturated condition. And the presence of air and solids is a dry condition. That's all. And for a four-phase diagram, nothing but for four-phase, this amount of for four-phase, some part of the water will be frozen. So we can take it as a volume of ice. So V ice, and we weight of W ice, for weight of W ice will be taken as we can take it like that. However, frozen soil, we are not dealing much about the frozen soil. I've only discussed about three-phase and two-phase diagrams. Okay, we'll directly go into the terminologies like void ratios. These are the things like void ratios, porosity, and everything. These are the parameters which tells about the soil condition in a mathematical data. So void ratio is nothing but it is a volume of voids to volume of solids. So volume of voids is E, it is termed as the E, and volume of voids to volume of solids. So we already know that. However, even for example, V is equal to VV by VS. While compacting to the greater extent, this VV will not be equal to 0. Even we are compacting at a very high, if we are compacting like whichever the force we are using, even heavy force, the volume of voids will not be equal to 0. However, it may reach 0, but it will not be 0 at any cases. So we already know that volume of solids is a constant parameter. Whatever the process we are doing, it will be there. So E value will not attain 0. However, for example, and I'll explain this terminology. So E value may greater than 0, but it can take any value. Not only E is equal to 1, E equal to 2, it may take any value. It's because that VV is comprised of volume of water and volume of air. So while the soil is, wait, I'll draw the diagram. This is volume of solids we'll take, and this is volume of water, and this is volume of air. So while if we add water into the soil, this level will be increasing, and at particular level, this VA will be vanished, and this total VV will be equal to VW. So at this condition, it is just a saturated condition. This is just saturated condition. So even after that, even after getting saturated, if you are adding water into it, what will do? Vs will be the same, but this Vw will be increased. So this Vv will be increased. So Vv will be very much greater than, Vv will be very much greater than, this Vv is final Vv. So final Vv will be very much greater than Vv initial. So Vv may change. So this VV may take value, even it can exceed the value of VV. So that's why E can take any value. Okay, VV is not a constant parameter. It can range it to any values. Even the soil get loosened, this value may change. So E can take any value. However, E is not only suitable. E will not take only 0. However, other than 0, it will take any value. So the range of E is simply this one, and greater than 0 and will not be equal to 0. So we can easily say that E is greater than 0. Simply, this notation has greater meaning in it. Next, porosity. Porosity, it is the volume of voids to the volume of soil. This is like while seeing a void ratio, we should note clear it is solids. It is volume of solids, Vs, which is constant. However, in porosity, it is total volume of soil. V is equal to Vs plus Vv. So it comprises of volume also. We should be very much clear about that. So eta is equal to Vv by Vs plus V. So that's why, for example, if VV is increasing, it's going to be, this factor is also going to be increased. So that's why it will not reach 100%. It will be less than 100%, and also it is less than, sorry, it is greater than 0% and less than 100%. However, I already told you that VV will not be equal to 0 at any conditions. However, if it is, if this value, if eta is equal to, want to be 100%, this value should be equal to this value. However, Vs is also a constant parameter. So at each and every condition, when Vv is increasing, the denominator will be somewhat higher than this, somewhat higher than the numerator. However, a soil without solids is not a soil at all. So the soil particle which is devoid of solid particles is not at all a soil. So this parameter will not be equal to 0 at any cases. If it is equal to 0, it is not a soil itself. Then it will go into fluid category and everything. So we are clear that. So now I understand. Now I'm clear that people will be clear about these notations. So this will be very much important. If they ask the range of, it will be useful for you to score a good marks. And then we'll switch on to degree of saturation. Degree of saturation is nothing but it is a ratio of volume of water to volume of voids. So here volume of water and to volume of voids. So it is very much clear that, and I'll explain the range in it. Okay. Volume of water. So S, I'll check it here. So S is equal to volume of water by volume of water. So when a soil is a dry soil, this volume of water is equal to 0. So for dry soil, VW is equal to 0. So VV is nothing but, so when it is a dry soil, the volume of voids will be completely, it is a volume of air. So VW will be equal to 0. So it can take a value of 0. And for a saturated soil, I'll see saturated. For saturated soil, S is equal to VW, and the void is also completely filled by water. So it is, the void is completely filled by water. So this may reach 100% or this value is 1. So that only the degree of saturation can attain the value of 0 and also it can attain the value of 100%. Next, air content. Air content is nothing but the ratio of volume of air to ratio of volume of voids. So likewise, like for example, we can say it is a counterpart of degree of saturation, air content. While talking with the water saturation and talking with the air content, it is degree of saturation. For example, I'll tell you. AC is volume of air by volume of solid, so which is VA and VB. So like that, for degree of saturation, we'll be telling it in percentage. For air content, the main convention of telling the air content is in the integers. Sorry, decimals and combined decimals and integers. So so AC is VV by VA by VB. So for fully saturated soil, VA may 0 and VV will become VW. So this value will be 0. So AC can attain a value of 0, and also for a dry soil, AC will be VA and the volume will also be A. So it can take value of 1. So this range, so air content can be in the range of 0 and also 1. It can take a value of 0 and also it can take a value of 1. And now we'll talk about the percentage of air voids. Percentage of air voids is nothing but it's a volume of voids to the soil. Whenever we are seeing it, the conditions we have to see it clearly. It is a total volume of soil. We must be very much clear about whether it is a volume of solids or volume of or total volume of soil. So eta is equal to volume of voids by volume. So likewise, for example, we'll take about for dry condition, VV will be completely filled by air and VS by VA. So this V for fully saturated soil, VA will be equal to 0. So it may sorry. So it can take a value of 0% and also 100%. It will be less than 100%. Or for example, eta is equal to V by volume of void, and it is a fully saturated condition VW, and it is VS plus VW. As far as the previously I've discussed, it will not reach 100%. However, it is less than 100% can be attained in it. And for 0%, if this value is 0, I think here it is wrong. It will be equal to 0. So I want to, it can take 0%, but it will not take 100%, because while if you're taking a dry condition, VA will be equal to 0, so only VS will be 0. So N can take a percentage of 0%. It can take, like, please take a note of it. It can take a value of 0%. And another important parameter while discussing in the definitions of geotechnical engineering is water content. And water content is nothing but weight of water by weight of solid. And I'll tell you in detail. So it is only WW by WD. For WW by WD, WD is nothing but we can easily write as WES for solids. So for dry condition, WW will be 0. For saturated condition, WW may even take value of greater than WS. So from 0, it can take any value. So WW can take any value. So this is the range of water content. And one more thing is that bulk unit weight of soil, and we'll be dealing about with the unit weight and density. And these are the important notations while calculating the behavior of soil. And bulk unit weight, the total unit weight, it is total weight of solid to the unit weight to unit volume of soil. So the total weight is comprised of WD and W water. Since WA is negligible to 0, so we are omitting it. So gamma is equal to WD plus WW by B. So it is a bulk unit weight. It is not like it is not saturated or it is not dry. It is a bulk, like whatever the soil present in the natural condition, it is bulk weight. Okay. And saturated, while taking saturated, it is in the weight is completely, it is a saturated weight. Saturated weight comprises of WS and WW. While taking the notes, WS can be written as WW. So WW and WS is both are same. And this is total volume. So this is a saturated unit weight. And dry unit weight is comprised only of WS by total volume. Okay, and this is a dry unit weight of soil. While combining all these things, for example, WSAT will have greater density, a greater unit weight, for example, greater unit weight than, so I can arrange in an order of W gamma SAT will be greater than gamma and will be greater than gamma D. So this will be the density values while taking this. And the common notations, common units used for density is kilonewton per meter cube. Sorry, this is unit weight. For density, we'll be using rho, which is kg per meter cube. For my convenience, I'll be dealing only with the unit weight soil. However, the formula which are used for unit weight can also support for density value problems also. And another two important things while studying geotechnical engineering, unit weight of solids and unit weight of water. And I can tell you that these are the true unit weights. While taking the previous thing, these are apparent because like it may take water, and these values may change according to the condition. However, these value will not change, and this is a constant parameter for a particular soil. Like for unit weight of water, it's a universal constant we know, and a unit weight of solids is a constant parameter for a particular soil. Since we are taking only about the weight of solids to the volume of solids. However, weight of solids will not going to be differ, and volume of solids will not be, volume of solid is not, it's a solid constant parameter. These are the universal constant for a particular type of soil, and this is a constant, it is a universal constant, and we know gamma W can be, it is the value is 9.81 kilonewton per meter cube. For my convenience, I'm using this parameter. Okay, and this is the value I'm going to use. And gamma W may also take value of 1 gram per cc also. Okay, these are the two values in two different unit system. And submerged unit weight. Submerged unit weight is the unit weight of soil which is under highly submerged condition. However, the water content is the volume of water is very much greater than the volume of solids present in the soil. It is called as submerged unit weight. So gamma submerged is equal to, it will, the notation of gamma submerged is gamma dash. It is gamma sat minus gamma W. Okay. Then we'll deal with true specific gravity of soil. True specific gravity of the soil is nothing but unit weight of solids of given volume to the unit weight of water of same volume. So gamma, this true gamma specific gravity is, we can guess gamma S by gamma W. So this value is also a constant parameter. So however, gamma S is nothing but weight of solids by volume of solids. So it's a true thing. It will not change at any condition. However, like it will not, like even if you add water into the soil, this parameter will not change. However, the apparent thing, the mass specific gravity is an apparent thing which will change accordingly. Like it will change for particular water content and particular void ratio, and it will change. Here we can say that gamma GM is gamma by gamma W. Gamma may be, it may be gamma sat or gamma dry, okay, or gamma, like unit bulk unit weight of a solid. However, this value, since it is a presence, since these things where it is the indication of presence of water in it, so this value will be always, this value will be always less than, this is gamma, sorry, this is gamma m. So this gamma GS will be always greater than gamma M. Okay, like take a note of it, it is very much important. Gamma true specific, whenever true specific gravity of a soil is always greater than the mass specific gravity of a soil. And we'll take the relative density. Relative density is nothing but it will provide the idea of how much the soil is compacted, how much the soil is compact in its natural state. Like for example, if we are compacting a soil, we can get minimum void ratio. But if we are loosening the soil, we can get a maximum void ratio, because E is nothing but E is equal to VV by VS. So if we are compacting, VV will be minimum, VV will be minimum. So at that time it will, E will be minimum. So if you are loosening a soil, VV will be maximum. So it may give rise to E max. So this is the range they are taking. So from E minimum to E max, it is the maximum, like it is the extreme limits. And by defining this extreme limits, they are locating the natural presence of a natural condition of a soil. So the E is the value. E is a value which will be somewhat, which have to be in this range of E minimum and E maximum. So they are dividing this range into 100 parts, and they are giving us an idea of how much dense the soil present in its natural condition. So ID is equal to, like this relative density is equal to E max minus E by E max minus E minimum. So when the soil is in, as I've already told, when the soil is in its loosest state, the natural E condition will be reaches E max, and when the soil is in the densest state, it will be E minimum. So while you substitute here E max, this value will be 0, and while substituting E minimum, this value will be 100%. So this will give an idea. And next slide will be, and this is the values of how much dense we can. If ID values is from 0 to 15, it is a very loose soil, and 15 to 35, it's a loose soil. And based on this, and 80 to 85 to 100, it is very much dense soil. And in this graph, it is very much noted that, like whatever the E value which are present in the natural condition will be in the range of this one. Okay, if E is E minimum, the ID will be 1, which is 100%. However, it may take any values here. It will not take. However, E which is present in the natural condition will not present in this area, which is not. This area it will not. So ID will not be greater than 100%. So we have to be very much clear that, so ID can take a value from 0 to 100%. However, it cannot go more than 100%. And these are the important relationship while solving the problems. So I would like to discuss about this one. So first formula is this. It is very much important, which is SE. I'll write SE equal to WG. And another formula is gamma D is equal to gamma by 1 plus W, and gamma is equal to G. This is a bulk unit. Gamma is nothing but bulk unit by G plus E S, which is saturate degree of saturation, gamma W by 1 plus C. For a dry soil, the degree of saturation will be 0. So since this term will become 0, and so that gamma and gamma W will be arrived. So which is gamma D equal to gamma G by gamma W 1 plus E. And for saturated soil, this S value will be 1. So it has become like this: G plus E gamma W by 1 plus E. And here gamma D, which is equal to Ws by W. So now I want to tell you another important relation, which is V1 by V2 is equal to 1 plus E1 by 1 plus E2. So we already know that gamma D is equal to Ws by V. So gamma D is directly proportional to V. Why it is that? Ws is a constant. So we are taking out this constant and we are inserting the proportionality. So V1, which is equal to 1 by gamma D1. So we are dividing it in the both condition. V1 by V2 is equal to gamma D2 by gamma D1. So we'll take this as 1. And here gamma D, we also know that another formula, gamma D is equal to gamma W G by 1 plus E. So this gamma and G, this is a true specific gravity. I've already told you. This is a gamma W, which is a constant. These both are the universal constant. So we can take this as a constant, and we are inserting the proportionality sign. So gamma D is inversely proportional to 1 plus E. So V is directly proportional to. So while relating this, so gamma D is inversely proportional to 1 by E, and while taking this condition, so V1 is directly proportional to 1 by E1. Sorry, V1 is E1. So V1 by V2 is equal to 1 plus E1 by 1 plus E2. It's a very important relation we'll be dealing. And so I've told you about the relation and everything. Now we'll switch on to the questions. And I've compiled some 4 or 5 questions, and we'll be dealing it in this session itself. And this is the question. In a wet soil mass, air occupies 1/6 of its volume and water occupies 1/3 of its volume, and the void ratio of the soil. So here VA is equal to 1/6 of its volume. Here the volume, whatever things the volume is volume of soil. So volume of soil, so total volume of soil. So hence we are categorizing it. VA is equal to V by 6 and VW is V by 3. So we know that VV is nothing but VA plus VW. We are substituting it V by 6 plus V by 3, which is equal to V by 2. So VV we know that, and VS we know that. E is a function of VV by VS. So while substituting this thing, E is equal to VV V by 2 by V by 2. So E is equal to 1. It's a very simple problem, and we can expect this type of problem in the exams also. And another thing, consider the following statements in relation in the given sketch. So volume of air, they have given us 0.2. So we can write it as VA is 0.2, and volume of water is VW is 0.3, and the volume of solids is VS is 0.5. So they have given weight also. They want to check these conditions. They want to check the condition of the soil is partially saturated, the degree of saturation is 60%, and the void ratio is 40%. What we have to check all this thing. So while checking the degree of saturation, we know that degree of saturation formula SR is equal to SR is equal to VW by VV here. VW by VV. So while substituting the volume of water, we know they have given us 0.3, and volume of void is nothing but VV is a combination of VA plus VW. So they have given VA as 0.2 and VW is 0.3. So hence it is 0.5. They have substituted 0.5 and they have found the percentage as 60%. So this condition is correct. And another. Next, void ratio. Void ratio, we know that void ratio formula is VV by VS. So we know that volume of VV value we know 0.5 and VS values we know that they have given 0.5. So E is equal to 1. However, they have given void ratio as 40%. It is not 40%. It is 1. So this condition is wrong. However, mostly void ratio, we will not tell void ratio in percentage, like mostly, but if at all mostly we won't tell void ratio in percentage. And also then water content. Water content, we know that water content is a ratio of weight of water to weight of solids. And the weight of water is, they have given 0.3 and the weight of solid is they have given us 1. So it is a 30%. So this parameter is correct. And saturated unit weight. Saturated unit weight is known that gamma sat is equal to weight of solids plus weight of water by total volume. So weight of solids they have given and the weight of water they have given and the total volume they have given, it is 1.3. Total volume they have given here, so we can use it as a, by this we got this 1.3 gram per cc and it is also correct. So the option is 1, 3 and 4, so it is B answer is right. Okay. Next problem, they have given the dry density of soil is 1.5 gram per cc and if the saturated water content is 50%, then its saturated density and submerged density. Okay, so they have given gamma dry, just gram per cc. Gamma dry is nothing but weight of solids by total volume. And like whatever, whenever you are solving a problem, just try to write what are the formulas you remember related to that, and so that only we'll be able to get an idea like what are the parameters we need and what are the parameters they have given. So by that only we can solve a problem in geotechnology. And they have asked for saturated density, they have asked for gamma sat. Okay, so gamma d and gamma sat they need, and they also need submerged density. So while combining gamma sat and gamma d, we know a formula which is gamma sat is equal to gamma d 1 plus w. So they have given gamma d and water content we know, so that we can solve gamma sat. So they have substituted gamma d is 1.5 and 1 and 0.5 for water content, and they have given an answer of 2.25 gram per cc. And for we know that for saturated for submerged density, gamma sat minus gamma w, and gamma sat value is 2.25 and minus 1 will be gamma sat. So the right answer is saturated density and sub. First thing is saturated density and then submerged. While selecting the formula, we have to be, while selecting the answer, we have to be careful whether what is the order they have given, so that we have answers. Okay. And next problem. Here they have given saturated and dry density of the soil as this one. So while taking gamma sat is 2000 kg per meter cube and gamma dry is 1500 kg per meter cube, and the water what they has is water content of the soil. Okay, so we have to think, so which are the formula which associate gamma sat, gamma dry and w. So we already know a formula which is gamma sat is equal to gamma dry into 1 plus w. So while rearranging this, after rearranging this formula, we'll get a right answer of just 33%. This is the right answer. This is how we have to solve a geotechnical problem. So if you simply, we have to assess what are the conditions they have given in the problem, and with that condition, what are the expecting parameter they are asking for the parameters. We have to first categorize those things, and then we have to analyze what are the formulas related to that. For all the geotechnical problems, like whichever the problems or all the geotechnical, there's major 5 relations I have given here. This 5 relations, this one, with this 5 relation, we can solve any type of problems. The only simple thing is we have to rearrange and we have to find the problems. So as of now, the basic parameter definitions and everything is over, and one more sum is there. Here the soil sample weight is 0.8 kg. So soil sample total weight of soil is 0.18 kg. Okay. And the volume, total volume is 10 cap minus 4 meter cube. What are the notation used should also be very much careful. This is V. Okay. And the dry unit weight, so gamma D is 1600 kg per meter cube and is mixed with 0.2 kg of water. Then the water content in the sample will be, so they are mixing an additional water to this to the soil mass. So they are expecting what is the total water content in the soil. So whatever the thing they are at, so WW which is added to this weight is 0.02 kg. Okay, we'll start with the problem. So while taking this, they want to find out the water content. So water content is nothing but W is equal to weight of water to weight of solids. So first thing we need to find out is weight of solids. So while finding out the weight of solids, we have a parameter which is gamma D, which is a function of Ws by V. Okay, this Ws is nothing but what the thing we want to find out the water. So while substituting this 1600 to its original volume, we'll find out the original Ws. So I have already told you that Ws will not change at any condition. So the Ws is a constant parameter. So from this next step, the initial water content present in the water can be found out, that initial water content, because while calculating while calculating the water content, WW is must. So for WW, the additional water content we know, which is 0.2, but the initial water content we have to find out. So that only by subtracting it from the original weight, W minus Ws is equal to, the original weight is 0.18 kg minus Ws is 0.16. So initial weight of water present in it is 0.2 kg. So and then we are adding some additional 0.2 kg. So the total is 0.04 kg. Okay. So the final water content is nothing but the WW will be 0.04 to the weight of solids is 0.16. So it is 25%. The answer is B. Okay. Okay. Up to now we have discussed about the basic terminologies and properties of soil, and I've discussed various various notations and various properties of soil to be taken into account. These properties and these definitions will give you a mathematical idea of a behavior of a soil. And the major thing I would like to revise is void ratio, the air content, porosity, and everything, and unit weight. These are very much important for calculating, and those areas are much expected area for the exams. And next we'll be switching over to the properties of soil. And this properties of soil can be divided into two different categories. One is index property, another is engineering property. And the index property is nothing but it's a physical property in which we are dealing with the grain size distribution, relative density, and consistency limit, like how the soil behaves for its physical conditions. And engineering property is nothing but its capacity for permeability, compressibility, and shear strength. Okay. And first of all, while calculating the index, we'll deal in detail about the index properties. While taking index properties, the first thing is grain size distribution. The grain size distribution is that it will give an idea of how much, like what is the diameter of the soil particle present in, and what are the diameter of the what are the particle sizes present in a mixture of soil. But soil is a particle which comprised of all all the range of soil particles. So we need to segregate and we need to get an idea of how the soil is. So we need to mathematically transform the soil into a mathematical parameter, so that we are using a grain size distribution chart. The grain size distribution can be found out by two different methods. One is sieve analysis and sedimentation analysis. The sieve analysis, we can do it for the particle size whichever the size is greater than 75 micron. So sieve analysis mainly employs the gravitational force, and it separates the gravitational force and vibrational force, separate the soil particles based on its sizes. However, the sedimentation analysis uses the terminology, uses the for example, uses a settling velocity. It mainly uses settling velocity of a particle size, and it also uses gravity, but still the settling velocity will be the major driving forces in the sedimentation analysis. The sieve analysis will simply vibrate it and we'll take the sieves out of it so that we can easily. But for the sedimentation analysis, mainly meant for 75 micron, the soil particle whichever is less than 75 micron. Okay, mostly the sedimentation analysis will be done for fine grained soil, and the sieve analysis will be done for coarse grained soil. The fine grained soil may have clay nature or plastic nature. For example, if a soil particle which is derived from rock based mineral, so for example, if a rock is crushed and those soil has been used now, it may have size particles less than 75 micron. But if a soil which is occurring in some clayey regions, it will be having plasticity. However, the soil which is derived from the rock will not have any plasticity. So the sedimentation analysis may done for plastic soil, and also it may not done for elastic soil without any plastic nature. Sedimentation analysis, in doing the sedimentation analysis, the thing we are mainly using is hygrometer. In this hygrometer, the particle, like the soil whichever is passing through 75 micron is mixed with 1 liter of water, and dispersing agents are mixed with that, and we'll be placing the hygrometer in it, and based on this height of this hygrometer. So while placing, for example, first for an hour the particle will be scattered in the water, and when the time goes, based on its diameter and based on its own weight, and this due to the gravitational pull, the soil particle will try to settle down in the bottom. So that the density of a soil, the density of the soil here will be, density of the soil water will be less. So this hydrometer will tend to alter its position in the water. So based on the position of hydrometer, those reading has been recorded, and with that we are analyzing the soil size distribution. And this is the particle size classification chart. And we all know that clay particles will be very much lesser than 2 micron, and the silt particles ranges 2 micron to 75 micron, and the fine silt and everything will be ranges from this thing, and the sand is ranged from 75 micron to 4.75 micron, and these are the gravel thing. Gravels are from 4.75 mm to 80 mm, and the cobbles are 80 mm to 300 mm, and the boulders are which is greater than 300 mm. And the human eye can see a particle size of 60 micron. So we can see a portion of silt. So 60 micron will be ranging here. So we can see a portion of silt, but we cannot see a full range of silt. And a single clay particle, we cannot see a single clay particle with our naked eye. Okay. And gradation of soil. Gradation of soil is one more important phenomenon of classifying the soil. Gradation of while gradation of soil, it is called as well graded, poorly graded, and gap graded. Well graded soil will be comprising of like all the range. A soil which comprises of, like for example, it may ranges have clay particles, silt particles, soil particles, and cobble particle, boulder particle. If it comprises of all the range, it is called as well graded. So that only a well graded soil will have higher shear strength when compared to other types of soil. Because, like for example, if a bigger soil particles when come closer to each other, the voids will be generated nearby. So those voids will be filled by the particle whichever whose diameter is less than this thing. So these combined matrix, this matrix developed in the well-graded soil will be tight and intact when compared to the other type of soil. For example, if we are using a uniformly graded soil, for example, a soil which comprises of only one type of soil of same diameter. For example, the soil is comprised of 0.3 mm particles. So those particles have only 0.3 mm size solids particle. So the gap formed between these solids will not be those voids will not be occupied by another solids. The voids will be intact. So this soil will have lesser shear strength when compared to the well-graded soil. So while in construction, we'll be opting only for the well-graded than compared to the uniformly graded or gap graded. Gap graded is nothing but that soil will be devoid of some particular portion. For example, it may have all the range, but it may devoid of some range. So that some range, if it divides of some range, the voids filled by those missing particle will not be taken place. So the shear strength of those soil will also be very much less. So the poorly graded is nothing but it is not only the uniform graded, the gap graded is also called as poorly graded. So we can take it as a two different classification, well graded and poorly graded. In poorly graded we have two different criteria. One is uniformly graded and another is gap graded. While seeing this diagram, we can come to an idea of how the graphs will be. Say, for example, take this graph D. This graph D will have a particle size ranging from 0.001 to 100, like for example, for nearer to some 30 to 40 mm size. So it will have a range. It will have all the range from here to here. So this will be a well graded soil. Okay, this will be the most well graded. So yeah, so we can take. Okay, and we'll take A. So this has a greater range. However, A is also well graded, but see, it will has a particle range only from this to this particle. So this soil, this A is also well graded, but it is not a it will not have any coarser particles because it is not having any so it will be it is a only fine grained soil. It is not a coarse grained soil, so it is only fine soil. This D graph is having a both fine grained soil and coarse grained soil and everything. Let's see E. E is completely devoid of fines. It is not having any fines, so it is not fine. It will not have any fines. And it is started from fine grained soil to coarse grained soil, and also it is some gap graded. This portion, it is not having any soil particle in this portion, hence it is a gap graded. Okay, and this B graph. This B graph is starting only from 0.1 mm size particles, and it is devoid of this range of fines. It completely devoid of fines, even though it is a. So here it starts from here and it has start from here and it is completely this range. It has well graded in this range, but it is devoid of fines. And this one, this is the interesting graph. C. C is a uniformly graded soil. Okay, this is a uniform. It has one type of soil which has a diameter one in this range. Okay, and while seeing the graph, we'll be able to classify it whether it is a well graded or poorly graded. But without seeing a graph, by mathematical data, we can capture the capture whether it is a well graded, poorly graded. We can capture. For that, we are using a two different terminology. One is coefficient of uniformity, and another is coefficient of curvature. Coefficient of uniformity, CU is equal to 60 by D10, and CC is D30 square by D10 into D60. And the D10, D30, D60 is nothing but it is that the particle diameter at which the particles, the distribution of particle, which is 10% less than. For example, this is I'll tell you in this graph. This is we'll take this graph. So I'll take this A graph, and this A graph here will be, so this size, the size whichever here, like I'll take for example 0, 0, 5. I can take, like I'm simply taking 0.005. So this value will be the D10 for this A graph, because less than only 10% of the soil particles will be less than this size. Okay, and for D30, let me take 0.008. So D30 will be, I'll take D30. So for this A graph, D30 will be 0.0. From that we can say that from this side. This is the size below which 30% of the soil is present, soil mass is present, and D60 is this one. I'll take it as 0.0, say 5, again 5. Again 5. So this is the, here D60 is 0.05, D30 is 0.08, sorry 08, D10 is 0.005. So this is, by these values we can find out the coefficient of curvature and coefficient of uniformity. So while substituting these things, we'll be having CU and CC, and they have given that. The CU values will be very much high for well-graded soil, and it is very much low for poorly graded soil. And for well-graded soil, CC value will be 1 to 3. 1 to, it will be ranging from 1 to 3. 1 to 3, and another parameters that C, when C is equal to 1, it is uniformly graded soil, uniform soil, and for when CU is 1 to 4, it is poorly graded soil, and for well-graded soil it is 4. So for well-graded soil, CU should be greater than 4, and CC should be between 1 to 3. The parameter, it is B. Okay. And next is consistency. Consistency will tell about the amount of water present in the soil, and how much the soil behaves to the how the presence of soil how the water presence make the soil to behave. The consistency can be taken into plasticity, and consistency and plasticity is nothing but the soil can modify to any shapes when the addition of water takes place. And Atterberg's limit, we know that there are 3 types of limits, which is liquid limit, plastic limit, and shrinkage limit. Liquid limit is a liquid limit is nothing but the soil will try to behave like a liquid, and it try to flow when particular amount of water added to it. And plastic limit is nothing but when amount of water content is present in the soil, that soil can be deformed to any shape, and it can take any shape, and it will not behave like a rigid soil. And shrinkage limit is nothing but this is the minimum volume occupied by the solids. Like, no, it's not minimum volume, like it is the limit at which the soil exceeds from just saturation to oversaturation. For example, let's see, these are volume of solids, volume of water, and this is volume of air. When we add water, when the volume of water V water is increased, this level will be increased to this level. So V initial will be, that is the minimum water content, it will remain as V initial itself. And after that, even after adding the water content like water, this VV will be increased. This VV initial value will be increased. So the minimum level up to which the water can return, up to which the soil can be said as just saturation, that is called shrinkage limit. Okay, we'll stop here for this session, and from next session I'll be discussing this Atterberg's limits in detail, and we'll solve some problems also. Thank you.